Hello students, welcome to Spectra Educational Academy. In this video, I am going to explain answers for VSAQ in the chapter Magnetism and Matter. Before we get the definition of magnetic declination, and there is one more question, question number dip, angle of dip and magnetic inclination. So let us try to understand how the geographic meridian, how magnetic meridian will be for the earth. So just you take so this is the external structure of the earth. Then if you take a plane, call this as geographic meridian. So this is the plane joining both geographic north. This is geographic north, this is geographic south. So perpendicular to which there will be geographic equator. So say this is geographic, this particular plane is called geographic meridian. And this is called geographic equator. Then now let us draw one more plane. This is going to be magnetic meridian. So what you can say, otherwise you can draw little neat also. So this is magnetic meridian. So you can say this is earth magnetic north. So this is called magnetic meridian. Perpendicular to which there will be magnetic equator. This is going to be magnetic equator. Then, so the plane connecting earth magnetic north and south, earth magnetic south, is called magnetic meridian. Suppose a bar magnet is suspended. So earth behaves like a magnetic field, a bar magnet suspended. So the south of the bar magnet align at the north, earth magnetic north, whereas the north will be here. So the magnetic lines of force are from north to south. So these are the magnetic lines of force, you can say. So they start from North Pole and ends at South Pole. Yeah. So now let us try to get the definitions of first question. Magnetic declination. So the angle between geographic meridian and magnetic meridian. So just to understand like that, placing a paper in adjacent to which another paper. Yeah. Like this. You treat this as magnetic meridian. This is geographic meridian. The angle between these two, so let us say theta, is called declination. Next, moving to the, there is one more question, sixth one. So let us complete the definition of magnetic inclination or dip. So this is resultant magnetic field of the earth. If you go with some del operator, So the angle between. So how can you define the inclination or dip? The angle between resultant earthmagnetic field. Resultant earthmagnetic field with horizontal component of earthmagnetic field. Horizontal component of earthmagnetic field. So that is, you can say this is, if you resolve B into two components, this will be B cos theta, B cos del, you can say. So you'll have to write B, you can write B is equal to BH cos del. So this is the information for inclination or dip. So there is a numerical here, question number 4. The horizontal component of Earth's magnetic field at a certain place is 2.6 into 10 to the power of 5 Tesla, and the dip angle is 60. What is the magnetic field of the Earth at that location? So this is nothing but resolving B into two components. So BH will be equal to B cos pi, and BV is equal to B sin pi, B sin del in particular. So therefore, so we need only BH equal to B cos del. BH is equal to B cos del. So they mentioned horizontal component in the question. So it is 2.6 into 10 to the power of minus 5. Horizontal component mentioned. And B, they are asking us to find out cos del. So this is 60. So cos 60, you might know it is 1 by 2. So the resultant magnetic field will be 2.6 into 2, 5.2 into 10 to the power of minus 5 Tesla. Now, moving to the answer for second question. Bar magnet of length, so it is magnetic length of 0.1 meters with magnetic moment 5.4 ampere meter square, placed in a uniform magnetic field of intensity 0.4 Tesla with its axis making an angle 60 with the field. What is the torque of the magnet? So just get back the formula. Torque is equal to mb sin theta. M they mentioned in the question. So magnetic moment, that is 5.4 into the magnetic field is 0.4 Tesla. Then here this is 60. Sorry, making an angle 60. Making an angle 60 with the field. Its axis making an angle 60. So sin 60. So sin 60 is root 3 by 2. So roughly this is going to be 0.2. Then 5.4 into 0.2. So 5.4. So 1000, it means this is going to be 1.08. Okay, just multiply 5.4 into 0.2. So you'll get 1.02. This is multiplied with the root 3. So just you multiply and get the answer, but don't forget to mention. So torque is measured in Newton meter. Then moving to the answer for next question. What happens to the compass needle at Earth's magnetic field? So therefore, get back the formula. Just now we have written BH is equal to B cos del at the poles. Yeah. At the poles, the BH is 0 because the reason is dip angle will be 90. So therefore, cos 90 is 0. BH is equal to 0. So therefore, magnetic compass needle can show any direction. can show any direction. Yeah. So moving to the next question. Classify the following material with regard to the magnetism. So the materials are manganese, cobalt, bismuth, copper. These are the materials you have to classify it. Yeah, there is one more question. So with in addition to the above material, cobalt, there is also one more this one material, nickel. So you have to classify them. So out of all the materials, so first let us try with diamagnetic. So this is answer for question number 8. So question number 5 and 8 almost similar except nickel. So first diamagnetic. So out of which diamagnetic are copper and bismuth. Then next, coming to the paramagnetic. Manganese and oxygen. And last, ferromagnetic. So bismuth over, oxygen over, copper over, manganese over. So cobalt and nickel. So this is the answer. Moving to the answer, question number 7. What are the units of magnetic moment, magnetic induction, and magnetic field? So first, magnetic moment. So it is denoted with the letter capital M. It is measured in ampere square meter. Then next, coming to magnetic induction. Magnetic induction in general, we go with the letter B. It is measured in Tesla or Weber per square meter. Then next, magnetic field. So it is in general is denoted with letter L. It is measured ampere per meter. So moving to the answer of next question. Question number 9 and the third one are similar. So they do not show any deflection. And otherwise they can align to any direction. So because horizontal component of the Earth's magnetic field will be 0 at the poles. Next, so question number 10. Magnetic lines of force. Magnetic lines of force forms continuous closed loops. Why? Because so this is the bar magnet, say north pole and south pole. Inside the bar magnet, the magnetic lines of force are from south to north. Externally, magnetic lines of force are from north to south. So that is why, therefore, what you can write is inside the bar magnet, magnetic lines of force are from south to north, but outside they are from north to south. So hence these are called as closed loops. Next, question number 11. Already you got the answer for this question in the previous chapter. So magnetic moment associated with solenoid, M is equal to N number of turns, and A is the area and I is the current passes through. So A can also be written as pi r square, area of each turn of the solenoid. So likewise there are N turns. Then okay, so what direction of compass needle points at the poles? Which needle to be used at the poles? Okay, then so the magnetic compass needle, answer you can directly write. The magnetic compass needle magnetic compass needle will align according to the poles, according to the poles of the magnet. The two ends of the needle get attracted in opposite direction. In opposite direction of the magnetic poles. Yeah. Next, moving to the next question. State Gauss law for magnetism. So the magnetic flux. This is answer for question number 13. The magnetic flux in any closed surface. Magnetic flux in any closed surface is equal to 0. So magnetic flux we can write B dot ds. But we are saying that this is 0. So therefore, even you can also write pi is equal to, so the line integral with B dot ds. This is equal to 0. Yeah. So magnetic flux to any closed surface is 0. Magnetic flux through any closed surface is 0. Yeah. Now, last question, 14th, Curie temperature. So the Curie point, you can say the Curie temperature. Curie temperature of a ferromagnetic material. Above which Curie temperature of the ferromagnetic material, above which, just orally write, above which it loses the property to possess, magnetism in the absence of external field. Students, thank you very much for watching my video. The Curie temperature of a ferromagnetic material is the temperature above which it loses to possess magnetism in the absence of external magnetic field. Yeah. So once again, thank you very much for watching my video. In my next video, I'll continue with VSAQs, and of course, this is optional, electromagnetic induction. Yeah. I'll continue with VSAQs in electromagnetism. This is safe side only. But in general, they are not asking. Nowadays, they are not asking any VSAQs from electromagnetic induction. Okay. But I'll continue with VSAQs in electromagnetic induction. Thank you very much once again. But don't forget to share and subscribe with your friends and relatives.